This video is going to give an introduction to the concept of continuity. To start, we'll use an intuitive definition and work our way to refining it a bit. So pictured here are continuous functions and their graphs. So we have on the left f of x equals x squared, our parent parabola, and that function is continuous over its entire domain, so all real numbers from negative infinity to infinity. The intuitive definition of continuity is that if you were to trace this curve, you would not have to pick up your pencil. You don't have to lift your pen from the paper. Same thing with the middle function. This is the absolute value of x, our parent absolute value function. It is also showing continuity across the entire real number line. And then the last one is the function logarithm of x, which only exists from zero for values greater than zero for positive values of x. And we see it is continuous over its domain. So it is continuous for values between 0 and positive infinity. Discontinuities, places where we are not continuous, can show up when we take a look at some other functions. So if we see a jump or a hole in the graph, then there is likely a discontinuity found there. So looking at these three graphs, the first graph on the left is the graph of a rational function, 1 over x minus 3. And in this graph, we have a left branch or a left arm of the rational function that points down towards negative infinity as we approach the value 3 on the x-axis. And then for values greater than 3, that function is approaching positive infinity as we approach the value 3 from the right. This function is continuous on its domain. However, the value 3 for x is not a part of the domain, simply because if we were to plug in the number 3 for x, we would have a 0 denominator. So it is not continuous when x equals 3, but it is continuous over the rest of the real number line, which is its domain. So it's continuous from negative infinity up to 3, union with the interval from 3 to positive infinity. The middle graph gives us, and the right-hand graph both give us examples of some piecewise functions, but they're doing a little bit different things in their graphs. So the one in the middle, we have a rule that is a straight line, a linear function, except when x is 2, we are using the value 5 as our output. So this function would not be continuous across its entire domain because it is continuous everywhere except there's one place when x is 2 that I have to pick up my pencil from the page to draw that dot and then return to the line. So it is not continuous when x equals 2. We have that jump up to a positive 5 value for our output. However, it is continuous elsewhere on the graph. So from negative infinity up to 2, union with 2 to positive infinity. The last graph, another piecewise function, shows us one rule that is a linear function to follow until we arrive at the x value 1. We do not include the value 1. If x is 1 or greater, we follow the second line. So this function has a discontinuity when x equals 1. We see that jump. So we would say that the function is continuous for all the other x's because as I trace along the function, I see that I have no need to pick up my pencil except for in the one place when x equals 1. So we would have continuity from negative infinity up to 1 and from 1 to positive infinity. However, in between those intervals at the value 1, it is discontinuous. We have a discontinuity. Okay. So now we're going to refine our definition of what continuity means. We're going to get a little more precise than just saying, oh, does it have a jump? Is there a disconnect? Do I have to pick my pencil up off the page? So let's work on a little definition. If we have a function, call it f, it is continuous at a point. We'll say when x equals a. So it is continuous at a if 3 things hold true, three properties. So first, f of a must exist. So you have to be allowed to plug the number a in to the function. If it gives you a zero denominator or something along those lines, then this property is failing, it does not exist, and the function's not continuous at that point. The second property is that the limit as x approaches a on this function has to exist as well. So we can check that. If we use graphical approaches, we can check that. If we use algebraic approaches, we can check that. So we need to check that the limit exists, meaning the limit from the left is equal to the limit from the right. And then the last property is that the limit from property 2 needs to be equal to the value from property 1. If those two are equal, then we have a point where the function is continuous. It will be continuous at a. If we're looking to determine not for a single point, but over an interval, we say a function is continuous over an open interval if it's continuous at all of the points in the interval. So these properties have to hold true for all of the numbers in that interval, not just one single value. Furthermore, if the value you're interested in is an endpoint, we can define continuity at the endpoint if we allow for a one-sided limit rather than the two-sided limit. So we'll see if we get into an example like that. All right, so let's look to check these three things on some particular functions. So the first example I'd like to show is going to use the function f of x equals, it's a relatively simple function, it's a linear function, 2x plus 3, and we want to know, is it continuous at x equals 4? So to check if it's continuous, we first want to check the property that f of 4 exists. Am I allowed to just plug in the value 4 to this function? Does it result in a zero denominator, a square root of a negative, some issues? The answer here is no. This is a linear function, which is a type of polynomial. Polynomials allow you to plug in any real number. 4 is a real number. So yes, the value f of 4 does exist. Then we would want to evaluate whether the limit as x goes to 4 on this function exists. Again, because this is a polynomial function, we know that the limit exists, and it's as simple to evaluate the limit as plugging in the value 4 into the function. So yes, the limit does exist. And then we check to see if these things are equal to each other. So the limit as x goes to 4 of 2x plus 3 is equal to 2 times 4 plus 3, which is 11. But also, if I plug in f of 4, I'm going to get 11 when I plug in 4. So yes, they are equal to each other, and we have, it is continuous at the point 4. When x is 4, the function is continuous. Let's see a second example. So the second example, the function's a little more complicated. It's a piecewise function, but the individual rules in this piecewise function are still linear functions. So let's say we have a piecewise function where the first rule is 1/2 x plus 3, and we do that for x less than -2. And then a different rule is x minus 1, and that rule is valid when x is bigger than or equal to -2. So the question is, f of x continuous at x equals -2. So at that point where we switch rules, is this function continuous? If we graphed this, we could just look to see, is there a disconnect? Is there a jump? But I'm trying to kind of stress a little bit the algebraic approach here. So first, we want to know that f of -2 exists. Am I allowed with one of the rules to plug in the value -2? And the answer is yes, the bottom rule. When I plug in f of -2, I'm going to get out -2 minus 1, which is -3. So it does exist. Then we would look to see that the limit exists. So does the limit as x approaches -2 exist? That's a slightly more complicated question, and if we're not using a graph, the way we would tell is to evaluate the limit from the left and the limit from the right. So the limit as x goes to -2 from the left would be values smaller than -2. That will follow this top rule. So that's going to be 1/2 x plus 3, where we can substitute in the value -2 to that polynomial. 1/2 times -2 is -1. -1 plus 3 is +2. If this limit exists, we should get the same value when we check the limit as x approaches -2 from the right. When values are bigger than -2, when they're on the right, we use the bottom rule for x larger than -2. So we would have -2 minus 1. Because again, polynomials, we can plug in that value to evaluate the limit. -2 minus 1 is -3. These do not match. That means the limit does not exist. The two-sided limit does not exist. Since that property has failed, we do not have continuity. This function f of x, this piecewise function f of x, is discontinuous at x equals -2. And we'll look at one more example of a piecewise function and observing continuity at a particular point. So this piecewise function will have a linear piece to it, but also a quadratic piece. So the first rule is -x plus 3, and we're going to use that for x less than or equal to 2. And the second rule we use is x squared minus 3, and we'll use that for x values greater than 2. So that is our piecewise function, and we're looking to see, is g of x continuous at x equals 2, at this changing point. As I mentioned in the previous example, you could graph this and just take a look to see if the graph has any jumps or disconnects. Without the ability to graph it necessarily, or without the desire to graph it, we can also evaluate this using algebraic methods. So if it's going to be continuous when x equals 2, we need g of 2 to exist. So g of 2, if I plug in the value 2, I'm going to follow that top rule. We'll have -2 plus 3. -2 plus 3 equals to 1. So yes, it exists, and it's equal to 1. The second property is that the limit as x goes to this value 2 on our function g of x must exist. If that exists, the limit from the left and the limit from the right will be equal. So I'll take a look at finding the limit from the left. So the limit as x goes to 2 from the left of g of x, that means I'm plugging in numbers smaller than -2. When x is a value smaller than -2, we use the top rule. So we'll have -2 plus 3, which is 1. Now, we should, if it is, the limit exists, we should get the same value, 1, when we approach from the right. So we're going to find the limit as x approaches 2 from the right of this function. When x is on the right of the value 2, it's bigger than 2. So we would use that bottom rule, which tells me 2 squared minus 3. Now 2 squared is 4, minus 3 equals 1. So we do get the same value from the left and the right, which means that limit exists. And the last property is that the limit as x goes to 2 on the function, which we now know that limit is equal to 1, needs to be equal to the value we would get from just plugging the number 2 into the function. And indeed it is. We got 1 for that in the very first check. So yes, this function is continuous at x equals 2. Where the previous piecewise example, we looked to find if there was continuity where our interval, our domains rules changed, and the answer was no. So this graph, if we were to graph it, should have two pieces where they line up. They meet each other at a point when x is 2. The previous example would not. We would have two separate pieces.